basic definitions, we are going to see the next method, residue method, singularity. A singular point of a complex function f of z is a point in which the function is not differentiable, that is not analytic, right? Both are same. Example, you can take 1 by 1 minus z, f of z is equal to, when z is equal to 1, the function become 1 by 1 minus 1, 1 by 0, infinite. Is not defined, right? So you cannot differentiate. Therefore, the function is not analytic. Therefore, z is equal to 1 is a singular point of this particular function. F of z is equal to 1 by 1 minus z. You can take 1 by z, simple function. When z is equal to 0, 1 by 0 becomes infinite. So z is equal to 0 is a singular point of f of z is equal to 1 by z. So you can take another function, f of z is equal to e power z by z, right? Same, z is equal to 0. This is infinite. F of z is equal to e power 0 by 0. Therefore infinite. So undefined at z is equal to 0. Z is equal to 0 is a singular point, right? Now, types of singularity. So mainly there are three types. One is isolated, removable, and essential, right? Now we'll see isolated singularities, because we need isolated singularity to find the inverse Z transformation, right? So we are concentrating on only on the isolated singularity. An isolated singularity of a complex function is a singular point. First, it is a singular point, right? And there is no other singularity nearby it. Isolated means it is the only singularity in that particular region, in the small region. Other than that, there is no other singularity nearby it. That means, except that particular point, the function, given function is differentiable at all other points around that particular point, right, in that region. Then that point, that singular point is called isolated singularity. I am isolated in a room means I am the single person inside the room, no other person with me, right? Same concept, right? Isolated singularity, right? There is no other singular points, the small neighborhood of that isolated singular point. Neighborhood means a small circle, small region around that particular, very small region, that particular point, singular point, right? A point z0 is an isolated singularity of f of z. If f of z is analytic, every point in a small neighborhood around z0 except z0. Right? If you are drawing a small circle around that particular singular point, in that region the function is differentiable except that particular point. Right? Example, you take sin z by z. Z is equal to 0 is a singular point. So you draw a small circle around z is equal to 0 with center 0, right? So in that region, sin z by z is differentiable except that origin, right? Z is equal to 0. Then z is equal to 0 is an isolated singular point of that function sin z by z. Similarly, you can take f of z is equal to z plus 1 by z into z square minus 4. Consider the denominator. When z is equal to 0, the function undefined, so singular point. So around z, you put a small region, neighborhood, taking 0 as a origin around that. In that region, f of z is differentiable except z is equal to 0. So don't take big one, right? With radius, small radius. Radius is 0.5, 0.3, 0.2, right? Like that, right? That is also a big one, 0.002, right? There are so many circles you can form, right? That is called a neighborhood. In that region, f of z is differentiable. So z is equal to 0 is an isolated singularity. So next factor, z square minus 4 is also in the denominator. So using a square minus b square formula, it can be written as z plus 2 into z minus 2. So z equal to 2 is a singular point. Z is equal to minus 2 is also a singular point. So similarly, you can take a small neighborhood around z is equal to 2. So the function is differentiable except z is equal to 2 in that particular region, in that small circle. Similarly, you can take a small circle with center z is equal to minus 2. In that particular circle, and the function f of z is equal to z plus 1 by f z into z square minus 4 is differentiable except that z is equal to minus 2. Therefore, z is equal to 0, z is equal to 2, z is equal to minus 2 are isolated singularities for this given function, right? Next, some standard results. There is a relation between Z transformation and Fourier transformation. So it is given by f of n, which is equal to 1 by 2 pi I integral over c f of z power n minus 1 into dz, where c is a circle with center origin and radius sufficiently large. Take the radius of that particular circle sufficiently large to include all isolated singularity of f of z, right? Is a closed contour. C is a, right? Cauchy's residue theorem. Based on this theorem only, we are going to find the inverse z, right? So f is analytic in and on C, right? C is a closed contour, and it is not analytic except, right, for a finite number of isolated singularity within C. Then the integral of the function f of z over C around C is equal to 2 pi I times of the sum of the residues of f of z inside C. That is, the integral over C f of z dz is equal to 2 pi I into sum of the residues of f of z inside C. Here we can take, instead of f of z, capital F of z into z power n minus 1. So integral over C f of z power n minus 1 dz is equal to 2 pi I into sum of the residues of f of z into z power n minus 1. Replace f of z by capital F of z power n minus 1 inside that closed contour. Therefore, we need f of n, small f of n, which is equal to 1 by 2 pi into 2 pi I into sum of the residues of f of z inside C. So 2 pi get cancelled. Therefore, f of n is equal to sum of the residues of f of z into z power n minus 1 inside C, right? So f of n, which is equal to, right, sum of the residues of. So we need to find the residues of capital F of z into z power n minus 1 in the problem, right? Thanks.